Hello. In previous videos, we studied systems of linear equations and we know how to solve such systems. Given that homogeneous systems of linear equations is a very small topic in the textbook, but I would like to make a separate video because they are really important. Okay, so let's talk about the definition of homogeneous systems. You have system of linear equations right here. If all three coefficients are zeros, so you have a homogeneous system. Okay. Other than that, everything is almost the same with general systems of linear equations. So, if you want to write the arithmetic matrix of this system, basically you have 1 0 column. Sometimes you don't need to write it. Does that make sense? So basically you have to work with the coefficient matrix in here. Right? That's the first thing. The second thing I want to mention is homogeneous systems always have solution. Right? Uh, it's obvious that 0 is one of solutions. Okay, let me write it down. If I have x1, x2, xn, so we have 0, 0, and then 0 here, n times 0 vectors in this case is one solution. So that's why homogeneous systems always have solution. Okay, so we know that a system of linear equation may have only one solution, may have infinitely many solutions, or may not have any solution. But in this case, homogeneous system already have 0 solutions, right? So we need to classify or clarify how many solutions homogeneous system may have. So maybe just 0 solution, which is trivial solution. Sometimes we call trivial. If homogeneous system has another non-trivial solution, that means that system has infinitely many solutions. Okay, so that is all about homogeneous system. But we will use homogeneous systems to solve the general systems of linear equation. Let's consider the following example. We have x1 minus x2 plus 3x3 equal to 0. 2x1 plus x2 plus 3x3 equal to 0. For this system, we have the following matrix: 1, -1, 3, 2, 1, and 3. I don't need to write 0, 0, because that is just 0. Whatever you do, that is still 0. So I just write the coefficient matrix. Okay, let's get the reduced row echelon form from here. So I will multiply the first row with -2, add to the second. Okay, then I get 1, -1, 3, 0. So here I will get -2 with -1 is 2, 2 plus 1 is 3. -2 with 3 is -6, plus 3 is -3, right? Okay, and from here I might simplify, I might divide the second row by 3, right? Or we say multiply with 1/3. I will get 1, -1, 3, 0, 1, -1. Okay, now we need to do backward, right? So I need to get reduced row echelon form. We have echelon form like this. Now this is our leading element 1. I will make this guy become 0. Just multiply the second row by 1. Okay, and then add to the first one, and we do that in the first row. We have 1, 0, just add to that. So I have 2 right here, and then 0, 1, negative 1. This is my reduced row echelon form. Okay, then from here I can write general solution. As you know, we have 0 and 0 right here, right? Basically, we have that. Then from the second equation, I got x2 equal to, we have x1, x2, x3, yes. x2 equal to x3, right? Okay, let's not skip steps in here. So I write x2 minus x3 equal to 0. And then I get x2 equal to x3. That is from the second equation. From the first equation, I get x1 plus 2x3 equal to 0. From here, I get x1 equal to negative 2x3. Okay, and then we can rewrite the general solution, x1, x2, x3, as, you see, x1 is equal to negative 2x3. I get negative 2x3, right? x2 equal to x3. I write x3 in here, and x3. So in the general solution, you may see, yeah, we still have one x3, right? The guy x3 as parameter. You see that? And if you take x3 out, you get x3, negative 2, 1, and 1. So basically, what is this? Geometrically, this is the general solution of the homogeneous system, right? General solution of the original homogeneous system. And actually, all solutions are generated by one vector only. By this vector only. You see this? By negative 2, 1, and 1. So you have negative 2, 1, and 1, and you multiply with any x3, you get a solution of that homogeneous system. And when x3 is equal to 0, you get trivial solution, right? So the original system has infinitely many solutions, and all solutions can be described by this way, okay? So, you know, what is a vector, right? You see, this is a vector. Let's say this is a vector. This is origin, negative 2, 1, and 1. So this vector determines some straight line, right? Some straight line right here. And this is just directional vector. So the solution of the original system may be understood like, yeah, this is all points on this straight line. Is that correct? All points on this straight line. But that is easy to understand. You know why? Because, what is this? This is a equation of what? Of a plane, right? This is another plane. So, you know, two planes may intersect by a straight line, or maybe parallel, or maybe the same, right? But in this case, they intersect by a straight line. That's it. Agree? One more thing I want to mention. These two planes contains the origin. That means this straight line also pass through the origin. You see that? When x3 is 0. So you have the origin in here. Okay? You know, this is very interesting, because when we study vectors, when we study vector spaces, or you know, basics or everything else, you see actually only such things, only such, you know, straight lines are subspace. Okay? But we'll talk about that in the future, not right now. Now, I would like to consider another example from this guy, okay, from this example. Now let me change this a little bit. I will change 0 right here, okay? So suppose that you have the following system: x1 minus x2 plus 3x3 equal to 1, and 2x1 plus x2 plus 3x3 equal to 2. Okay. Of course, from here you might think for this system you have the corresponding homogeneous system x1 minus x2 plus 3x3 equal to 0. And 2x1 plus x2 plus 3x3 equal to 0. And we know this system has solution as x3, -2, 1, and 1, right? Okay, so how do you think? Can we find the general solutions of this guy from this? Is it possible or not? All right, so if you want to see that, we need to solve these systems in the usual way we know, okay? I will just copy everything from here, but I will rewrite the arithmetic matrix. I have 1, -1, 3, 1 in here, okay? And then 2, 1, 3, and 2. So I will not explain in detail. I just write -1, -1, 3, 1. The second guy is 0, 3, -3, and 0. Okay, and then I divide the second row by 3. I get 1, -1, 3, and 1. I get 0, 1, -1, and 0 in here. And then I get 1, 0, 1, -1, 0. And this guy is 1, 0 is 2, he's 1. You see? All right, so from the second equation, I still have x2 minus x3 is 0, or x2 equal to x3. From the first one, I get x1 plus 2, x3 equal to 1. From here, I get x1 equal to 1 minus 2x3. All right, so let me write general solution. I have x1, x2, x3 equal to 1 minus 2x3, x3, and x3. Now let's separate them. This is equal to 1, 0, 0, minus x3, -2, okay, plus -2, 1, and 1. Now with this, we did such, process in the past. So, in here, I just separate, right? Free coefficient, I have 1 in here. In this, we don't have any free coefficient, so I get 0. Here is also 0. And then I separate x3. I take x3 out. I get this vector. Now look at this. Let's compare these two guys. This general solution and the general solution of the corresponding homogeneous system is right here. So you can see actually they have some relation, right? They have some relation. All right, so what is this? This component is the same, right? In two formulas. What is 1, 0, 0 in this case? Let me plug 1, 0, 0 into the system. But we don't have to plug that, when x3 is equal to 0. So you have one solution of the original system, right? That means 1, 0, 0 is a solution of the system. So I hope you can guess the structure of the general solution of our system of linear equations. So here's the structure. The general solution of this guy has two components. The first component is some solution plus the solution of this guy. Homogeneous system. You see? So That's why homogeneous systems are so important, right? In order to solve the original system, you may solve the corresponding homogeneous system, and then you just try to get some particular solution of the original one, and then add pop them together, and you get the general solution of your system. There is another way to understand this idea. Look at this. If you consider R2, it's the XOR plane, okay? In here, if you have any straight line, let's say this straight line, okay? So I may obtain this straight line from some straight line here that pass through the origin, okay, that have the same slope. You see this? And then I can move this straight line to the left by some vector, or move off by some vector, or whatever. You see this? Whatever. You don't care, right? But I can find infinitely many vectors so that I can move this guy to get the one right here. Does that make sense? So what are these? They are some solutions of the original system, okay? They are some solutions, some particular solution. So you might have several partial solutions of the original system, but the solution of homogeneous system looks like this. That is just only one, right? Which pass through the origin. You see this? Homogeneous system always has solution. That is trivial. So that means, whatever you have, right, that should contain the zero, the origin. And then if you have some vector, means some particular solution, you may shift your solution set of homogeneous system by that vector, and you get the general solution of the original system. If you move to three-dimensional space, this is almost the same. Okay, this is almost the same. We just saw that right here. You have some vector, you see this? Some vector, and that is not only vector, that is the whole straight line. You see, we have straight line right here. Let's say this is -2, 1, and 1, okay? And this vector determines some straight line, and then you have solution, you have particular solution 1, 0, 0. So what is 1, 0, 0? You move this, right, along the x-axis, right? You move along the x-axis. Let's say this is the x-axis, and here you move along the x-axis, right? This is 1, so that's what you get. And this is the solution set of your original system. Okay, this is 0. Does that make sense? So I hope that you understand all examples in here and the importance of homogeneous systems. We will have chance to go back to this topic in the future, but we need to understand this really well. All right? Thank you for watching, and see you in the next video.